All right, so good afternoon, everybody. My name is Susan Perkins. I am the Martin and Michelle Cohen Dean of Science at the City College of New York, and it is my great pleasure to welcome you all to this first Division of Science Distinguished Alumnus Award presentation. So I just joined City College in January of this year, and part of my attraction to this institution and to the Division of Science in particular was its rich history of successful and noteworthy alumni. 10 graduates from science and math from City College have gone on to be Nobel Prize winners. But also a major attraction to me was the role that City College plays in being a continuing force in propelling students from New York and beyond, many of whom are first-generation students, into rewarding careers. This mobility engine, as it's often called, is a complex machine that involves our faculty, our staff, our infrastructure, and our students, both current and former. These parts work together to provide experiences that are mutually beneficial to all. We learn from each other, we grow with each other, we lift each other up, and we celebrate our accomplishments and our successes together. So today begins a new tradition in celebrating the successes of graduates of the Division of Science who have taken their knowledge, their hard work, and their desire to make their communities, their countries, and this planet a better place. Dr. Arden Warner, our first recipient, is a truly outstanding and deserving inaugural alum for this award, and he was an easy choice for us when I suggested that we begin to bestow these awards. We had hoped that we would have him back to campus in person so he could see our new buildings, see what other changes we've made, meet our students and faculty, and he was slated to be our keynote speaker for the second annual Day of Science. Unfortunately, COVID-19 had other plans, and that in-person event was canceled, at least for now. That, however, did not mean that we needed to cancel his award, and so I'm very pleased that we're able to do this today, even in this virtual format, and I thank you again for joining us. We will be holding several other similar events this spring to honor some of our other outstanding alumni, and I hope you can join us for those as well. Before I turn this over to Provost Liss to say a few words, I wanted to thank a few people. First, the Dean's Office staff has been so very helpful as we've put this event together. Laurent Mars, Elizabeth Rudolph, Cindy Gonzalez, and Frank Pace in particular. And Millie Roth gets special recognition for her initial idea to invite Dr. Warner to speak at the Day of Science. She's long been a very big fan of his. I want to thank Joanne Huang and our communications department, Anthony Achille and Nana Abaye for their help with getting this award together and setting up this webinar. And finally, I want to thank some of you who gave us really generous donations that have helped support this event. And I want to give you our utmost gratitude for your generosity. So I'm now going to turn this over to Provost Liss to offer his welcome and congratulations to Dr. Warner.
Thank you, Susan. You know, I'm not sure whether you asked me to speak at this event because I'm provost, because I was dean of science before you, or because I spent a good fraction of my career working at Fermilab. I was at Fermilab from 1984 until about 2007. I wasn't employed by the lab. I was at University of Chicago as a postdoc working at Fermilab, and then for a long time at University of Illinois. So I spent a good part of my life driving up and down 133 miles, I happen to know, from the parking lot at University of Illinois to Fermilab, where I worked on the CDF experiment for many, many years. So I have a great deal of fondness for it, and I'm really happy that this first award is going to Dr. Warner, and I really want to congratulate you, Arden, for being the recipient of this inaugural award. And Susan, I want to thank you also for inaugurating this award because it's a wonderful idea. And I'm happy that this is happening on behalf of the college. And I'm really happy to see a physicist winning the first award. And I see the chairman of the physics department smiling at those words. So it's, you know, it's a great thing for the college on the one hand, because we are so proud of our graduates, and we know that they can do whatever they want to do, wherever they want to do it. And it's a great thing for Fermilab also to have this connection with the college. And this award in particular, I think, speaks to Fermilab's mission in the world, which, as when I, my work there was in, basic high energy physics, which is what the lab was built for. But the lab is so much more than that. It's an engine for innovation and technological development. And I think you're going to hear from Dr. Warner a specific example of that that's really important. And for those of you in the audience who don't know, Fermilab was the highest energy accelerator in the world for a long time before the Large Hadron Collider at CERN took over. But it really invented the development of superconducting magnets on an industrial scale. And that's allowed the accelerator at Fermilab to flourish, the one in Geneva to flourish. But for the everyday person, what it's done is made magnetic resonance imaging devices, MRIs, inexpensive to build, and they're in every strip mall in the country now. You can go and get an MRI. And that's a spin-off of the development of the accelerator at Fermilab. So we're going to hear Dr. Warner talk about another aspect of the technological development at Fermilab. And I want to also say that I learned, and just before we started here today, that he's collaborating with one of his colleagues at Fermilab, who happens to be my first student from when I was at University of Illinois. So congratulations, Dr. Warner. It's great to have you here with us today. I wish we were on campus, but when we get back, you're going to have to come and visit. So thank you all for coming today.
Thanks, Tony. And I will confess that I asked you to give some remarks for all three of those reasons. So it really was a perfect example of that. I neglected to thank one person. I did that on purpose, not because I forgot him, but because I want to invite him to just address us all. And that's David Covington, who is our executive director of the City College Alumni Association. And I want to give him my appreciation for being supportive of these new awards that we're doing. And so I'll just ask him to say a few words as well.
Thank you, Dean Perkins. Good afternoon, everyone. It's an absolute pleasure to be here to help inaugurate this new series focused on distinguished science alumni. We have so many alumni to be extremely proud of. As you mentioned, I have the distinct honor of serving as the executive director for this alumni association, one that can trace its origin back to our first graduating class. Back in 1853, members of that first class meeting in the chapel of our original building on 23rd Street forms the Associate Alumni of the Free Academy. Over the years, of course, we've grown, incorporated, and changed our name, but today the Alumni Association has 15 local affiliate groups, 10 active chapters around the country, and with a mission that's trifold, to generate and sustain meaningful connections with alumni, to celebrate them, support current students, and of course, to promote this great college. So we're a membership-based independent organization located on the campus. And if you're an alumnus and you're not already a member, please, or if you just want more information on us, our upcoming events, we have an oral history project in play right now, or on our alumni recognition awards, such as the prestigious Townsend Harris Medal. I invite you to learn more at ccnyalumni.org. Put that in the chat. By providing opportunities such as this for alumni to share their work or to reminisce, volunteer, connect with each other, donate and pay it forward, the association ensures, as it has for 167 years, this cycle continues, that a new generation of hardworking, grateful City College graduates will go out into New York City, the nation, and the world and change it for the better. And this is such as Dr. Arden here has done. And we will hear shortly about his novel approach to tackling one of the most devastating environmental threats we have today. So, and you, Dr. Arden, your alma mater has particular reason to be proud. Congratulations to you, and thank you for sharing your work with us today. Without further ado, I'll hand it back to you, Dean Perkins. Thank you all.
Thank you, David. I just want to point out one other quick thing, and that is if you do have questions as we go forward, there's a Q&A function at the bottom of your Zoom window. And the man I'm about to introduce will be fielding those questions as we go along. And that is Dr. Vinod Menon, who is professor and chair of physics, and he will be presenting Dr. Warner for us and taking your questions. So, Dr. Menon, please.
Thank you, Susan. And thank you all for coming. We have a great attendance today. And so we're really delighted to have Dr. Warner here, who is the first recipient of the Distinguished Alumni Award and in the Division of Science. And being the chair of physics, of course, I'm even more excited because this is the first one and it's from physics, as Tony mentioned. So I also want to thank Dean Perkins for initiating this award. This is a great effort from the division. And Dr. Millie Roth for suggesting Dr. Warner, or nominating Dr. Warner, which was very easy to decide on. Just a quick introduction to Dr. Warner. You're going to hear a lot about his work. Dr. Warner got his bearings in spectroscopy at City College. He was a class of 1989 BS in physics. Worked with Professor John Lombardi from the chemistry department where he did spectroscopy. He followed that with graduate studies at Stony Brook in accelerator physics and completed his PhD in '95. And then he started at Fermi Labs, where he leads a team currently responsible for what's called the Machine Protection Systems for Proton Improvement Plan 2 project. Well, to put it simply, it's building a state-of-the-art system to study tiny particles called neutrinos, which can help us understand the universe better. But what has also fascinated Dr. Warner lately has been his work as the founding partner of Natural Sciences LLC, a company that came out of Fermi Labs, and now he's partner of the company, which uses an innovative idea from electromagnetic forces to remediate oil and climate spills in our oceans and waterways. As we are all familiar, there are numerous of those happening, and this idea of using electromagnetic forces to remedy this is one that has been appreciated by the community. And in this role, he has helped remedy water spills all around the world. And this technology is called EMOP. It stands for obviously electromagnetic mop. And this technology has been patented, and this is the topic of today's discussion. He has won numerous awards, but most recently he's won the Barbados Golden Jubilee Award for Innovation and Technology, given in recognition for contributions to innovative energy research in solar and wind energy. And so without much ado, Dr. Warner, it's a pleasure to have you here, and we look forward to hearing about your work in cleaning our environment. Thank you.
Thank you very much to all of you. I really am very appreciative of this award and to making a contribution to City College in any way possible. I just want to say a few words about my experience at City. I immigrated from Barbados, as was mentioned. My mother had called me and told me that she found a place where I could pursue this thing called physics that I kept talking about, and that it was a place where you could get a reasonable and affordable education. And I remember once I finally got to City College, it represented everything that she said. And the mural in the Great Hall, for me, represents the story of America. The idea that no matter where you come from, there was this idea that you could get an education. And that reasonable education is what afforded me to be here today. City College also offered me an opportunity to do research very early. And I met some wonderful teachers and people doing great research. This is the most important thing to me, because it was very early that I started in this program. And I realized that you don't just consume information, but you also can create it. And this idea of being able to explore the world was, innate in me, but City College really helped to foster it. I went on from City College because of many influences there to Brookhaven Laboratories. Professor Roth was very instrumental in getting me engaged in research. And I also want to say a shout out to Michael Engber, Professor Engber, who's retired now. He was my mathematics professor, and he also helped me to foster my interest in research. So I'm talking today not about accelerator physics per se, even though a lot of the ideas came out from working at Fermilab. As Professor Liss mentioned, Fermilab is a very innovative place, and they have encouraged me in my ideas. And this idea I want to discuss today is one that I thought would be a good general topic because it transcends the physicists, and it goes to everyone who lives in this world who wants a good environment. The idea that oil spills or chemical spills could destroy the ecosystem, I didn't know that it would be such an important idea, that I would be that interested in it until something happened. So my presentation today is basically going to be telling you the story of how I got involved in this idea and why I think it's important. But it also shows that the idea of City College, the idea that you can explore the world and contribute with an education, or with the idea that you can get involved and help in some way. That came out of City College. My colleagues at work always ask me, why do I always think that I can find a solution? And I said, well, we all think that, but I brought that spirit specifically from New York and from the City University of New York. And that has never failed me. It's always difficult, but it's always interesting. So I'd like to start to give this presentation and tell my story with the idea that although this is not about accelerator physics, that it's about ideas. I hope everyone can see my screen. Is my screen being shared? Can you say?
Yes, Arden.
Thank you. Okay, so I'm going to talk about electromagnetic remediation of oil spills. And I want to discuss what motivated me to get involved with the problem. And I want to talk about the fundamental concepts involved. And then the things that start to bother you once you start to get involved in a problem on this magnitude, whether or not your solution is scalable, whether there are unique features and advantages to it. So I want to go through those ideas. I also want to discuss the fluid dynamics, which is a fascinating thing, but I wouldn't spend a lot of time on it. I'll brush on these things. And I want to talk about the engineering applications and the implications of what we've been building. And also some spin-offs, the actual applications of the technology. I want you to also keep in mind that oil spills are not uncommon. They happen quite a bit. Very, very large oil spills happen every few years, but every day there are spills. And some of them are not described in the media because they're not affecting enough people. But every so often there are these oil spills that really affect many, many people. Actually, right now there's a spill going, potential spill going on in the Caribbean. And there's also been one in Mauritius during this time of COVID. So this is an image from 2010, and many of you may recognize it. Some of you, if you're students, might have been, I don't know, 8 or 9 years old when this happened. But this is a spill situation in the Gulf, and this is the leak. And this is oil that's coming from the ocean floor, a mile below the ocean floor. And this was the reason that I got involved. This oil spill went on for many, many months, for 3-4 months at this rate. And the oil was just building up in the Gulf of Mexico. Many people don't realize it or don't know, but at the same time that spill was happening, there was another spill going on inland. So that previous spill I showed you was in the ocean. It was the largest ocean spill in US history in the Gulf. But at the same time, a few months later, there was a large spill in the Kalamazoo River, and it was the largest inland spill in the USA. A pipeline had fractured and had spilled many, many gallons of oil into the Kalamazoo River. And this was very, very heavy crude oil from Canada. And heavy crude, as opposed to very light crude, can sink below the surface of the water when it spills. So it's not at the surface. And this sequence of events got me very interested. Not to mention working at Fermilab, the Department of Energy at the time was led by Stephen Chu, and the Secretary of Energy, Stephen Chu, had sent emails out to the national laboratories at the time asking for ideas and people to get involved in the spill. And that got me even more motivated. The real motivation, however, came from my wife, who asked me, after watching many days of them trying to put the leak out, what would I do? And I mentioned to her that I would probably try to magnetize it. The idea of magnetizing oil, of course, is not new, but I had a different idea, and that's the idea I want to describe today. The technology that is typically used in oil spills looks like this. It's usually booms, and these are passive booms. And this got me motivated to think about, wow, this is a device that's trapping the oil. It's not protecting the marshlands really, but then they have to come along and bring a device that could potentially clean the oil up once it's trapped. So it's a very passive situation, and my ideas went towards something more active, something that moved the oil, controlled the oil. So in thinking about those things, I asked myself, well, what forces are really at work in the oil spill? Can they be controlled to our advantage? What fundamental concepts would we need to scale? Because this was a spill where there were 210 million gallons of oil. This enough oil to encompass many Barbadoses, and it was quite a bit of oil. And at the end of the day, they only collected 5 million gallons of the 210 million gallons. So the other questions I want to know was anything that we would make or build or will have to be scalable and be efficient. Not everything that you scale up remains efficient. So what aspects of the problem also could we leverage? You're dealing now with waves, and you're dealing with oil sinking below the surface. You're also dealing with different chemicals in the oil, wildlife, and a number of ideas, a number of problems. So the most important thing though is that you want it to be environmentally safe, because most of these spills, they use chemicals, they use burning, they use all types of methods that are detrimental to the environment. Corrosic, for example, is a dispersant that causes the oil to particleize and essentially sinks. And then we have to depend on microbes to eat it. And it affects the fishery, it affects the ecosystem in general. So after my wife had asked me about this idea, what I would do, I went to bed, and I literally got up at 3 o'clock in the morning. And I went to my garage with this idea of being able to not just magnetize the oil, because oil has been magnetized before, but not to form a ferrofluid or anything like that, but to form what we call a colloidal mixture, colloidal suspension. And I went into my garage, and I'm going to show you some raw footage from that night. It's not cleaned up, it's very raw. And if I knew that this would have gone to the places that I had gone, I would have cleaned my garage, to be honest with you. But the idea was that I could take very, very small particles, iron oxide, for example, or magnetite, even better, since it's stable. And if these particles were put into oil, if they were small enough and light enough, they should form some sort of a bond with the oil due to what I now know are van der Waals forces and other forces. And the idea would be that these particles would be then attracted to a magnet. And if they also have a bond with the oil, then the oil would move as well. What I didn't know and what I realized from this image here is that I could see the oil clearly moving, but I could see places where I couldn't see the oil. But there is oil there. And this oil is moving around and being pulled towards the magnetic forces, even though it's very thin. It's a very thin sheen. So one thing was, what bond is holding these particles in the oil? Remember, these are iron oxide particles. These are 5 times more dense than the water. They're more dense than the oil, but the combination of the oil and the water, they tend to move. So that fascinated me. I started then to do a number of different experiments at home. And so what I want to get from this talk is that what I started with in a Dixie cup ended up being done in a national pool at a naval facility in 2.6 million gallons of water. And I'm going to walk you through that story to see how we got there. And I hope you find it fascinating. So I went on to look more closely at the particles and the oil. And I realized that I can not only can I put these particles in the oil, that these particles tend to stay with the oil. They also are held in with some forces, which we had to try to understand, and I'll go through the process of learning what those forces were. We could move and manipulate these particles, and therefore move and manipulate the oil. And this image here is showing a very simple example, but the thing that fascinated me here was the fact that you could move the oil in plumes, and that you could then extract the particles. Almost 100% for sure of these particles could be removed. So we started to do a bunch of extensive tests with this stuff. And we went on to look at all types of effects, like rheological effects, which are effects that allow us to actually almost freeze the oil in place because of the magnetic forces. What we were able to do is, and in this video, I'm not really cleaning up the oil as Bounty. I'm using that to protect my only magnet that I had at the time. And but you see, it took the oil off the surface. So these were questions that I had to ask and had to get answered. And these effects were effects that we ended up having to scale. So what I'm showing you now is all the different small effects that I measured. And then we started to try to quantify and understand these effects. And these effects led to the system, the final design system that we'll show at the end. So one thing we realized is that the hydrocarbons with low and high viscosities, we could test them and we could see if there was a difference due to viscosities or different properties of different oils. So we had to test a lot of oils. We had to look at surface tension effects and applications that had to do with the nature of the bonds between different octanes, different hydrocarbon bonds, which are very complicated and varied. So what type of oil would it work with and under what conditions? So we did lots of testing. In this situation, we are describing how we put these small particles in the oil, and they're randomly dispersed in the oil. And as we apply a magnetic field, of course, these particles will align themselves in the direction in the magnetic field. And orthogonal along the axis here, the fluid becomes more rigid, more viscous, because of these particles. These little particles essentially are little dipoles that connect. And that allows us to take the oil and almost freeze it and lift it. And this video is sped up for expediency, but essentially I'm oversaturating the oil with iron oxide particles. And then we're taking a magnet, and we realize is that this effect allows us to lift and move the oil from the surface. So we started to get a bit more scientific about this thing and move out of our garage a little bit. And I went to the director of our laboratory at the time. And I also went and spoke to another City College alumni, Dr. Letterman, who was the lab director emeritus at the time. And I showed them what I was doing to see if this was really had merit or if this was stuff that was just done all the time and wasn't effective at large scales. And what I got from them was encouragement. And I took then samples of this to other national laboratories to have them look at what was going on under a microscope. So what I'm showing here is the effects of these particles in oil. Here's a sample under a microscope, and the particles are randomly distributed. You apply a magnetic field, the particle aligns, but it also grabs the oil. The oil tends to cling to these particles. And that was fascinating. It was fascinating for several reasons. We did tests to show that when we put particles by themselves just in the water, the particles really just fall through the water. They don't stay there because they're heavier. You would expect if you put iron oxide in water, it would just sink. But we also noticed that when there's oil, even when there's a very, very thin layer of oil, even if it's on the surface or below the surface, these particles tend to stick with the oil. So over here, where you see particles gathering, there's oil there, even though you can't see it. You can see the yellow oil here, but over here, there's oil. And the rest of the particles fall through. So these particles are sort of also of a probe for finding the oil. And that was a very interesting effect. It meant that we could see the oil in some way, and even the sheen, even at the very small scales where it's not visible to the eye, you could actually grab onto oil. And it also was interesting because oil that sinks below the surface could also be acquired within reason. We started to continue to do many, many tests with different oils to understand the bond and understand the fluid dynamics. And we started to do various demonstrations to understand how various oil plumes and different oils would move. So here's a simple test where I'm taking an oil of known viscosity and I'm applying a small number of particles by hand. And we wanted to see if we could actually remove these particles from the oil and leave the oil behind. It turns out that the forces, the frictional forces and the bond is such that the plume always comes along with the oil. As a matter of fact, we know now that no matter how strong the magnetic field you apply here, the plume will come with the oil within reason. Now, take in mind there's no waves, there's no other external forces going on here. So right now we're just looking at the basic concepts and trying to build from there. Another thing that we noticed was that the oil, once it's seated, when you put oil in water, it tends to diffuse outward under forces, external forces, and due to viscous effects, they try to pull it together, but it tends to move out till it reaches some sort of an equilibrium. But we also notice that once we seed the oil with these small particles, which are micron size, and they'll get to the size and the scale of the particles, that the diffusion slows down considerably to the point where the oil does not spread. And this is the absence of external forces. So this is sitting right now in a Dixie cup and not really conclusive. We went on then to look at the environmental impact on what it would be in putting large amounts of iron oxide in the ocean, for example. And we realized that magnetite is already in the ocean. It's in the sand, it's in igneous and metamorphic rocks. And if you were to take a magnet and you went to any beach around the world and you pulled it through the sand, you would collect magnetite. Magnetite is a natural material. It's been around for many, many millions of years. It turns out that it's inexpensive. which was encouraging. And so the question we started to ask was, well, how would we really apply these particles, and what is the optimum size for these particles? What would we need to do to these particles? Do we have to make them hydrophobic, resistant of water to make them even better? What principles could we apply here? And how do you get it into a spill? So my initial idea was that you would inject it at the source of the leak and allow it to mix. And that was the original idea, to inject, instead of injecting golf balls and debris as they were doing in the Gulf, which was very impressive, by the way, because this was a leak that was, a mile below, and they had these robotic devices, and they had an arm coming from the surface that would inject mud and debris to try to close the leak. In principle, I thought you could inject magnetite, allow the oil to mix in the turbulence, and then you can use magnets to collect the oil. So the whole idea of how you would do this started to bubble in my head. And I started to investigate what particles we would use. And it turns out that particles on the micron size scale work very well with these van der Waals forces. You could use nanoparticles, but that introduces different effects. You're dealing with Brownian forces as opposed to van der Waals forces. And also, it turns out in the end that because the particles are on a micron scale, you can very cleanly separate them from the oil, because they're held weakly by these forces, but they're held strong enough that they form this bond that allow you to manipulate the oil. So we went on to think about, well, now that we know these fundamental principles, how do we scale up, and how do we automate this process? So I just showed you a lot of the fundamental ideas that went into the whole concept here. And now I want to look at the scalability and the practical engineering concepts that has to go to work here. And what are the figures of merit of a system? What would define an ultimate system? You can continue to scale forever, but there's a limit to how strong a magnetic field you could use, what a practical system. What would be the real fundamental figures of merit that would help you, an engineer, decide what to build? So we asked a bunch of questions, of course. What is the efficiency of the process? What type of oil types does it work on? We tested over 200-300 types of oil, but does that mean that it works on all hydrocarbons or all oils or all chemicals? We had to answer these questions. And would it be cost effective to build? So to answer these questions, we started to measure various internal forces, van der Waals network forces. We started to measure surface effects. We started to look at the electrochemistry and the hydrophobicity of the situation. We tried to solve issues related to wave actions, because now, so far, I haven't shown you any waves, right? So we started to go through that process. And this is a normal process with any idea. And keep in mind that all along, I'm thinking somewhere along the line, I'm looking to see the system fail. I'm looking to see what would break this idea and how to overcome it. So eventually we did all those tests we mentioned, and we started to get some professionals to really start to look at this oil and this fluid. And we started to look at it on larger volumes of water, larger volumes of oil. And we would inject these particles, and we would use magnets, and we would see how the oil flows, try to understand the dynamics. And this is a video taken by HBO, Vice. They came and they were interested in what we were doing, and they had professional photographers. So I got out of my garage, and we were able to try to understand the fluid dynamics and try to quantify. And then I started to get other physicists involved who would otherwise be doing other things. They saw what I was doing, they thought it was interesting, and they got involved. One of the fundamental things that I want to come away with here today is that even when you mix oil and particles together and then you throw it in water, the particles do not separate from the oil. The oil behaves normally like oil. So this is oil with magnetic particles embedded in it. And this is a simple a bar magnet, and you can see the fluid flow. The interesting thing here to me was that there's some very thick oil here. There's some very viscous oil, and there's some very viscid oil that's not very thick. And the thing that was fundamental to me was that this oil moved towards the magnet roughly at about the same rate. And it turns out that the rate is proportional to the gradient of the magnetic field, which is the force. And it behaves in a very Newtonian way. And the typical modeling that you would do for a fluid, you could simplify it quite a bit. So instead of solving very complicated Navier-Stokes equations and so on, I started with very simple dynamical Newtonian equations. And the answer to me, coming from my experience at Fermilab with designing and building magnets and working with accelerators, is that we really want to control the magnetic field, because the oil seems to just cling on to these small particles, and it follows the magnetic field lines. So the simplest magnet to build would be a solenoid. And the interesting thing about a solenoid is really just a coil where you put a current in it, and there is a magnetic field. The bluish lines here represent a magnetic field. And at the ends of the solenoid, you can see that there's a divergence to the field here. And so there's a gradient. So there's a force. So a particle over here would get pulled because there's a force, and get pushed because there's a force. And if we could couple that force to another magnet that was a conveyor belt or something that would then move the particles up and out of the water, then the dynamics are very different. And I say that because when it's in the water, there's very, very low surface coefficients. But when you remove it from the water to another surface, that changes dramatically by orders of magnitude. And the water gets rejected because it's not magnetic, and everything magnetic gets pulled along. So the idea was to build a magnet that was a solenoid, and a solenoidal field looks like what I show here on the screen. And the idea would be that somewhere outside of the solenoid, there's a force that pulls the particles in everywhere along the solenoid, and there's a force out here that pushes it along. So the idea would be that we get a series of boom to get away from the static boom I showed you, and build a dynamic boom, a boom that did work, and that would pull the oil and direct the oil along and inside its volume. And so the idea would be that we would build this boom out of solenoids, and you would energize these solenoids in some sequence so that while one is pushing, the other one is pulling, and then you hand off in the right order. And this was the idea behind building an electromagnetic boom system. So we started to look at the basic dynamics and look at the forces that would be involved here. You know, you have to deal with the viscosity and the buoyancy of the oil and all the forces, the magnetic force, the frictional force, the gravitational force, the force of buoyancy. And of course, there's a term that depends a lot on these frictional terms and the viscosity of the oil. So we started to model this idea and say, well, if we had solenoids that sat on the surface of the water, most oil tends to float on the surface, and some could float a little bit below, but the magnetic fields from the solenoid can extend slightly below the surface, depending on the strength of the magnetic fields. And that we realized that each molecule in the oil acts as like a spring to the next molecule in the oil. So it's like a simple harmonic oscillator, or pulling a slinky, really, where the bond is represented by the spring constant, the strength of the spring that's holding these things together. So this is why when you put a little bit of particles in the oil and you pull it with a magnetic field, the rest of the oil tends to come along. If it's very viscous, then that spring constant is very high. If it's not, then it's very weak, but it tends to pull it. It might stretch and shear, but it tends to move. So the idea would be that we would build a system where we have very thin solenoids, and we would pulse each solenoid on in some sequence that would create a magnetic force that would pull oil along the axis of the solenoid. And here's a model of such a system using magnetic fields. And you really look, and the magnetic potential is what really tells you how much oil you could actually capture within a given potential well, so to speak. So that defines somewhat of an efficiency. So we started to work on a system where we would turn on a solenoid, and while that solenoid was on, there would be some delay, a specific timing, where you would energize another solenoid, and while this other solenoid is ramping down, this other solenoid is still at a maximum field, so particles will continue to flow towards the magnetic force. So you really want a gradient effect. And because the frictional forces on water is very low, the only thing you have to worry about is wave action, and there's a solution for that. And what we essentially are doing is dependent on wave action, because waves tend to go in some direction. And if the direction is towards the direction you want to go, then it's basically helping you. So we really need to have a system that we can orient in the direction of the waves, so that the waves help and not be constructive. So we did some modeling, and each little plus sign here represents a little tiny piece of magnetic material, dipole, if you will. And this is the magnetic potential. And we say that it's like, it's like plucking a string, and the fluid will fall into these potential wells and will be moved along in the direction of the magnetic force. And this model is a model of several magnets in this configuration pulling and pushing oil towards its final destination. And that's out of the water. So
Arden, there's a question.
Yes, go ahead.
The question is from Dave Newman, and he wants to know if it's a systolic device.
It's somewhat systolic. The interesting thing about this system is that the viscosity of the system, the viscosity of oil, we found later this is independent. This system becomes very independent of viscosities, and we'll talk more about that later. And I'll show you the system working in reality in a larger scale, and you will sort of see that based on the magnetization, the amount of magnetization, the behavior can change and become either more efficient, or it can become not efficient at all. And we'll describe that. So just to get back to my point here, we wanted then to figure out, before we go on and build something based on this concept, we wanted a way to really model this thing. So here's a very crude, at my laboratory, we eventually formed a small spin-off company. Once we got patents on this outside of Fermilab, we took a license from Fermilab to go off and try to pursue this, to try to get this technology commercialized. And essentially, what happened here is that we wanted to verify that the system would work. So here are a representation of some solenoids, and the LEDs on here show which solenoid comes on and to what level of power. And what we essentially did is use magnetic balls that float and allow these balls to see if these balls. Now, take in mind that these balls are not oil. The frictional forces are very different from oil, but the idea would be that you could model the system and understand some of the dynamics. So this is just an idea to demonstrate that you could actually do this and sequence the magnets in correct order. The other thing we want to verify is that something that we knew. We figured that this thing would work on all sides, right? So particles, if these pink balls represent plumes of oil, they would tend to get in and want to get into the magnetic field, and they would form and flow along this train, and you'll be able to guide these particles. So that's it with balls, and we did that to understand the dynamics. And then we tried oil with different amounts of magnetic material. So here's a situation with a very low coefficient of friction, low particle oil ratio, low particle to oil ratio. And you see that when we energize the magnets, that the oil started to flow through the magnet. So then we know that this would work. Again, there's no wave action here, so we have to account for external forces still. We then went on to look at heavier oils, heavier fluids, more viscous, and the same effect. Of course, the spacing, what's not noticed here, that the gap between the magnets is very important. And I should say something about that. The spacing between the magnets is relevant because if the magnets are solenoids and they are spaced by a distance that's equal to the radius of the solenoid, then the field between the solenoids is very uniform. And that's called a Helmholtz arrangement, a Helmholtz coil. And we use that in the laboratory to really want very, very uniform magnetic fields to do calibrations and so on. But I want a gradient. So we have to move the magnets a bit closer, less than the Helmholtz distance, so that there is not a uniform field, but there's a gradient to the field. And you'll see that works out. Here's a visualization of the concept. And I'll let you watch this to see what we were envisioning. But the idea is that you would then have a large set of magnets. This is exaggerated, of course. But the idea is that these magnets, which by the way, are specially designed to minimize the potential field on the outskirts, but it's made of aluminum wire. And then when you energize them, you would pull fluid in, and this fluid would walk along the axis, entering at different points along the boom, the electromagnetic boom in this case. And at some point, it would exchange with a ramp, which was made with permanent magnets that would grab onto the magnetic fluid. And you would move that fluid into a container, and this container will have a magnetic field at the bottom that will pull all the fluid down and all the magnetite out. And all you would have is oil. And so that's the concept. So the engineering reality of such a system looks like this, where we have a set of solenoids, and these are the solenoids. Here's a module, and here's a system together. And here, this is us testing a group of these solenoids at the National Oil Spill Facility, where we want to test the entire concept. So I'll show you next what the prototype test look like, where we pour now not just a few liters of oil in the water, but we pour many gallons of oil in, and then we look at the effects and see if it works. So here's the oil spill facility. We got 2.2 million gallons of water in this large tank, and these are the underwater cameras going in, and I sped it up so you don't see the mixing and seeding process, but here's the oil coming in. And the oil, this is seeded with magnetite. Here it is 200 gallons of oil we started with in these tests. And we turn the magnets on and you see the effects. So this is looking from the bottom up. And look carefully, you can start to see the sky start to shine through. And there you can see the sky now. We can pull the oil in. And we'll show you next what it looks like on the surface. So a little quieter on the surface where the cameras aren't making all that noise. But you see that the fluid is being pulled and pushed, but it's making its way towards this magnetic ramp. And it comes up the ramp, and then the oil, it looks clear here because we're using a special type of oil where the viscosity is well understood. But you can see that the oil and the magnetite are coming up, and there's no water. The important thing here is that we're rejecting water. So this is not a skimmer. Skimmers collect water at the interface between the magnet and the ramp. Water is rejected, and the efficiency measure that the National Oil Spill Facility onset was that we were 97.2% efficient at separating the oil from the water. So that told us that we were on track and that we have a system that can clean up large spills. And large spills can look like this, but essentially we would seed large plumes of oil with a low velocity nozzle of magnetite, which doesn't rust even in salt water because it's already it's a stable Fe3O4, I think. And then you use a system to collect the oil and reject the water. And even if the oil has many different viscosities involved, it doesn't matter. If it's oil that's being coagulated, it doesn't matter. And if the oil is in the form of droplets, it doesn't matter. So this system is very effective at cleaning oil and cleaning water. I'm coming close to the end here, but the idea is that we have an environmentally friendly system that can be used to seed and collect oil, and then these particles can be reused. And the oil, in principle, can be reused. So those ideas also fostered other ideas, because oil not only spills in the oceans, it spills on other surfaces, it spills on marshes and rocks, it spills on animals, unfortunately, or animals get into the spills. And we started to look then at other effects, organic materials and absorbents. And we found that peat moss is a very fibrous organic material, and it has a very interesting property that when the water content in peat, sphagnum peat, for example, is below 60%, it becomes very, very hydrophobic. And when it's above, it's very hydrophilic. So in one case, it attracts water, and the other case, it repels it. But when it's hydrophobic and dry to a certain level, it also absorbs hydrocarbons, and it stops it from leaching back out into the environment, because it holds these hydrocarbons within its cellular walls, within its cellular membranes. And we also were able to figure out a way to magnetize the peat moss, so that these small particles would just cling to the structure, the fiber structure of the peat. And we were then able to use it to absorb not just oil, but chemicals and PCBs. And so here's a microscopic view of what peat looks like. And here is microscopic views of some electrolytic iron oxide. And here's the combination when you put them together. It really clings on to the peat. And not only does it enhance the ability to absorb oil and to confine oil, but now we can absorb it, you can collect it, and you can leak it, and can stop it from leaching back into the environment. And not only oils, but all the other carbons, all the other chemicals that comes along with it. So here's an example of how this works. And here's some really, really nasty oil. And we take the magnetized peat, and we apply it. It absorbs very efficiently, very quickly. And then we apply a magnetic force. Now you have a magnetic absorbent that works really, really well. And this can be spread and used and collected. And because depending on what you pick up from it with it, if it's crude or diesel, this becomes a fuel that can be used in incinerators. In Germany, for example, they would burn this for fuel. It's very efficient. I forget how many BTUs per, but it's fairly efficient. So that was a spin-off from the technology. And the other thing, spin-off, I want to leave you with is that we said we can remove this stuff from water. So clean water is taken for granted in many places here in the United States, but in some places it's a commodity. It's really difficult to keep water clean for consumptions in deserts areas and so on. So one of the applications of this system that I want to leave you with is that the system also lends to the ability to clean water. And this last video is sped up quite a bit because we let this run for several minutes. But here's oil in one of our tanks, and we put oil and we magnetize the oil. I left out the seeding process, but it essentially leaves you with I wouldn't drink it at this stage, but at least the oil, for the most part, has been removed. And most skimmers and other systems do not have this ability to clean at this level and at this rate. So there are many opportunities with electromagnetic applications of to oil spills, and I hope that you got a feel, at least a flavor for what this idea was and why we pursued it, and why we think that it's a viable process and has applications for the future. So I want to say thank you once more to the organizers of this Distinguished Award Series, and thank you for having me. And I hope that you enjoyed listening to what I had to say and that it was inspiring to some. The idea that you can start with something in a Dixie cup and end up with something that can clean and help clean the oceans of the world. I want to say a special thanks to Dr. Perkins, the Dean of Science, for helping to organize this. Dr. Menon for conversations we had and for his interest in me and my work. To Millicent Roth, Dr. Roth, who's always been in my corner and got me started in the National Lab System, and all those who participated in this event and contributed to the work behind the scenes. Thank you very much.
Thank you, Dr. Warner. Thank you, Arden. That was a fantastic talk. And for the students in the audience, I specifically want to tell this. It's amazing that what you learn in freshman physics, solenoid, through creative experimental skills can actually address some real world problems and something at such large scale. So it's really fascinating to see how something that you learn in class, which you sometimes think is just for the exam, can actually be used for something really important. So thank you, Arden, for bringing that up to our students and to everyone in the audience. We have a few questions. I'm just going to go down the list from the first one that I got. So one of the questions was, why not longer solenoids? Arden, you're muted.
Oh, I'm sorry. I always do that.
Okay. Yeah.
So the problem with longer solenoids is that the only thing that we need is the gradient effect. We need the gradient. So with a long solenoid, within the body of the solenoid, there will be a more of a uniform magnetic field and no gradient. With short solenoids, you get a pulse, a force that you can utilize. And if the solenoids are long, if something started to accelerate in, it was eventually decelerate probably before it got to the other end, and you have a buildup. So it wouldn't be most efficient. So there's an optimum size for the solenoid.
Excellent. The next question is, could the conductivity of the water alter the dynamics between the oil and the magnetites?
The connectivity of
the conductivity.
Conductivity.
Yeah, if the water is conducting. Yeah.
Yeah. Well, the water is conducting, but magnetic forces do not affect the water. So the magnetic forces only affect the magnetite and the things that cling to it, and the water doesn't cling to it. So it's not a problem. What we have to worry about with conductivity in the water is the electricity that you use to power the magnets. You don't want to, these magnets I showed you, this system is 6 kilowatts. So we had to design a system that checks for leakage current in your water, because you don't want people getting executed. If there's any leakage current, the system will shut off.
Next question is, could the system be adapted to remove oils from animals?
Good question. Yes, I started out this project while taking a dead bird. It was dead before I started. And we floured this bird's feathers with the magnetite after it was covered in very large amount of oil. The feathers of a bird are very hydrophobic. It sort of repels things. So there was a little bit of water trapped between the feathers and the oil. And when we did this, the oil came off readily. We didn't explore it too far because we want to pursue the main idea. But there's a professor in Australia, University of Melbourne, who's done extensive studies with removing oil and chemicals from animals and bird feathers using this idea.
Nice. The last question I have here is, has the EMOP been used in spill not under controlled conditions?
Good question. So we are at the verge of using it on spills. We are building systems now for prevention. We don't want to wait for spills to use this thing, but we tested it under very real world conditions at the onset facility. This is a facility which I glanced over here, but at this facility is where they test all the equipment that they use in oil spills, where they can generate waves. It's a 2.6 million gallons of seawater, ocean water, and it's very real. They test chemicals and burning and other methods, and this is where the tests were done. What we are working on now from a commercial point of view is a deployment system so that this thing can be deployed on naval vessels or vessels and used in the ocean. But our test showed it would be very effective, and we are now working on systems for deployment.
Excellent. Actually, I did not see the rest of the questions. They were just coming in. So another question is, can this be used as a substitute for fracking?
A substitute for fracking? But fracking is a different process. Fracking can lead to oily water, which is hard to dispose of. It's called produce water. So in fracking process, they really force water into fissures and cracks in the earth, and they extract the oil that way. So this is not a method for extracting oil, but removing oil from water or cleaning up after water has been oily water has been produced, so you can put the water back into the environment.
When do you think this process will be in actual practice?
This system? Well,
yes.
It's in practice now. We are building of several systems now. We are one of the things that we're hoping. COVID has delayed quite a few things, but many places have asked to have these systems ready before a spill. And also, I'm here in the Midwest and in the Great Lakes region. One of the biggest issues that they have to face is tar sand oils coming from Canada across the Great Lakes. When tar sand oil spills, it doesn't float on the surface. It floats below the surface because it's a heavy oil. And this is one system that can reach oil that's not just on the surface, but can be a foot below the surface.
Excellent. Next question, is there an optimum particle size for the iron oxide nanoparticles above or below the super paramagnetic limit? Probably the most important thing for the magnetite is to be the low cost, but surface modification can improve the affinity of the oil.
Yeah, that's a very, very good question. We have settled in on micron-sized particles for the environmental reasons. When you start to work with nanoparticles out in the environment, there's a whole set of rules that you have to worry about, inhalation and so on. That's one issue. So from an environmental point of view, using micron-sized particles as opposed to nanoparticles is effective. The other issue is that nanoparticles are held in the oil by stronger forces, atomic forces. Brownian motion affects particles. And we're not trying to make a ferrofluid. We're trying to make a colloidal suspension so that we can use normal magnetic forces, not necessarily normal, reasonable magnetic forces to remove the particles and separate them. nanoparticles are less easy to separate once you put them into the oil.
Excellent. So we'll come to the last question, which is whether the temperature has any effect on this process. For example, the Gulf of Mexico versus the Arctic Ocean.
Yes, another very good question. So when oil, for example, gets cold, it gets more viscous. And this system works better with more viscous oils for obvious reasons, in that it's a more rigid process. So in cold temperatures, this would be very, very effective. When oil is very viscid, very thin, when it's warmer, in some cases, it's the efficiency drops down a bit, but it still works.
And also, is the magnetite reusable?
Yes, definitely. The magnetite can be used, and actually, when we collect the fluid, we have and it's out of the water. We have a container that has a magnetic base, and it really just pulls the magnetite out of the oil, and the oil sits on top.
Excellent. Thank you so much, Arden, for answering all the wonderful questions and from some of our experts in the audience. I should also mention that both Professor Lombardi and Professor Engbar are in the audience. And if they had to say anything, they're welcome to speak up or ask a question, throw it on the chat or Q&A.
Let me just remind folks, I put this in the chat box, but if there are faculty or students or faculty who know of students who might want to do a meet and greet tomorrow with Dr. Warner, just shoot me an email. It's going to start at 12:30 and we can have a more dynamic conversation there, or anybody, any staff are welcome. Just shoot us a message and we'll make that happen.
Excellent.
Is there any? Before we get to that, and before everybody disperses, we're doing this again sort of virtually. So Arden, I sent you a few token gifts from City College, including a face mask, which nothing says 2020 like a face mask. And so we will be sending you this award. So this will be something to put up on your mantelpiece there. And for those of you who might not be able to see it, it says, for elevating the college through your significant accomplishments and professional service, the Division of Science at the City College of New York recognizes Dr. Arden Warner, class of '89, as a distinguished alumnus, November 16th, 2020. So
thank you much. I'll treasure it.
Well, it will be in the mail soon. We were a little bit behind. We were launching a new logo for the college, but we're very happy with that. And again, thanks Joanne Huang for all of her help there. It was such a delight to have this time with you. As I mentioned in the opening, we are just so proud of you and just so thrilled to have you be this first recipient of these new Distinguished Alumni Awards for our division. It's starting what I hope will be a great tradition for us to bring our alumni back to interact with our students and our faculty and our staff, to maintain that great connection and that love you have for City College. And we just thank you so much for sharing your story with us.
You're welcome.
So thanks all.